We ended our last session with a definition of Snell's law and defining Snell's law based upon the Fermat's principle. But before we continue on a little bit, just more about Snell's law sort of graphically. Again, as I mentioned, the refracted ray, so we're assuming light propagates through a air to glass boundary, is going to refract closer towards the normal if it's entering a media of a higher or denser index. So for example, let's assume this is an air with an index of 1 to glass with an index somewhere around 1.5. The refracted ray is going to have a smaller angle relative to the normal because, again, simply due to Snell's law. So if the index of the second media is higher, the ray refracts closer to the normal. So obviously, if the ray is going from a denser material to a lighter material, or from a high index to a low index, it's going to be refracted away from the normal. And we can see this graphically here. So planar surfaces makes it much easier to draw the normal at the point of intersection. So we can see here when we go from air to an index of about 1.4, the refracted angle is smaller, closer to the normal. Similarly, when we go from an index of 1.4 to an index of 1.9, again the ray refracts closer to the normal, smaller angle. But when we exit from the index of 1.9 into air, the ray gets refracted further away from the surface normal. Similar to Snell's law for refraction, we have our law of reflection, and as with Snell's law of refraction, the incident ray, reflected ray, and the surface normal at the point of intersection are all located in a common plane. The magnitude of the angle between the surface normal and the reflected ray, so this angle right here, is equal, again in magnitude, to that between the incident ray and the surface normal at the point of intersection. And if we simply look at Snell's law, if we're saying that theta 2 is negative, which we are because notice one ray gets rotated, if our incident angle, if we're rotating that ray clockwise to reach the normal, we're going to call that a positive ray. This ray we would have to rotate counterclockwise to reach the surface normal. That's what we would call a negative angle. So if the angles are opposite to each other, then the indices must be opposite to each other. So if you're doing a ray tracing calculation by hand, you'll have to keep that in mind if you're looking at rays that are intercepting a reflecting interface. If you're using a lens design code, of course, the software will take care of that for you. But again, the reflected ray, as with the refracted ray, is on the opposite side of the surface normal from the incident ray. So one last bit of housekeeping, if you will, before we actually get in to start talking more about first order optics and optical design and optical systems, is what we call a sign convention. And these are the sign conventions that are typically used in ray tracing. Just sort of keep these in mind or have these handy as we start discussing things in the future. But again, some basic conventions. If we're talking about light with a positive translation, traveling in a positive sense, we're talking about light moving from left to right. So if the light moves from right to left, then that would be a negative direction, if you will. A height above an optical axis, or above the optical axis, would be considered positive. A height below the optical axis would be negative. Distances to the right of a reference point are positive, and to the left of the reference point are negative. And when we get into first order optics, what we're going to see, we have several different reference points, and when we determine the sign associated with particular distances, we're going to have to look at what particular reference point are we talking about. If we talk about a radius of curvature value, if the center of curvature lies to the right of the vertex, then we're talking about a positive radius of curvature. If the center of curvature lies to the left of the vertex, then we're talking about a negative radius of curvature. An angle of incidence or refraction, which typically we'll call theta and theta prime, are positive if the ray is rotated clockwise to reach the normal. So if we think back on the law of reflection we talked about previously on the last slide, that's why I said our incident ray was a positive angle and our reflected ray was a negative angle, because one rotates clockwise to reach the normal at the point of intersection and the other rotated counterclockwise. Slope angles, that the angle that the rays make relative to the surface, are positive if the ray rotates clockwise to the axis or to a line perpendicular to an axis. An index of refraction is positive when light travels from left to right, and negative when the light travels from right to left. Again, similar to what we just discussed with the law of reflection. And this concept is probably the hardest one to deal with initially, but just keep it in mind. We'll see as we proceed exactly what this means. But object space and image space both extend to infinity in both directions. And again, that one will start to make more clear as we go through some of our applications and some of our definitions that are coming up. Okay. So that basically takes care of a lot of what I would call the housekeeping information. And now it's time to get into sort of the integral part of the class, and we're going to start with something that's referred to, as I've mentioned, first order optics. So let's start by discussing what exactly we mean by first order optics. First order optics are the parameters of effectively an ideal system, with one exception, that being chromatic aberration, which we're not going to worry about right now. Effectively, a first order system defines an ideal system, an aberration-free system. Okay? So again, when we're tracing light, tracing our rays, we're going to start with Snell's law. When the light hits an interface, you know the media that the ray is in, you know the media that the ray is going into, so N1 and N2 are known. You can calculate the index of refraction, the angle of incidence at the point of intersection relative to the surface normal, so the only unknown is theta 2. Okay? And it's sort of easy to calculate today. Okay? If I needed to know the sine of 30 degrees, okay, I can do that on my own. You know, that one's easy, it's a half. If I wanted to know the sine of 45, okay, that one I know too, that one's 0.7071, related to the square root of 2. Okay, those are easy. And the fact is, any angle today, that if you want to know the angle, the sine of an angle, you know, you pull out your, well, you probably don't have a calculator anymore, but maybe you have the calculator on your computer. Maybe you have a scientific calculator that you've put on your cell phone or your tablet or some other device. But historically, calculating things like the sine of some small angle or some angle was difficult. I will admit I'm old enough that in my high school days, and even some of the time I was in college, when I needed to know the sine of an angle or the cosine, what I had was a sine table into 4 or 5 decimal places. I could look it up and then I could do the math, typically by hand. Eventually calculators came along. But historically, it wasn't easy to do. So what was done? Okay? Remember, we've talked about the paraxial region, where we said that the sine of theta and the tangent of theta were approximately equal to theta, and that the cosine of theta was approximately equal to 1. If we look at the actual mathematical definition of how you would calculate the sine of theta can actually be represented as a Taylor series expansion, and we can see that expansion right here. So it's theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus plus, etc. And you can calculate the sine of theta to any necessary accuracy simply by increasing the number of terms that you use. When we talk about first order optics, what we're simply talking about is an approximation where we just use that first term, the linear term, in the expansion. So again, sine theta, we're going to approximate as theta. Tangent of theta, cosine theta, the approximations here as well. But that's what we mean by first order optics. So in the next session, what we'll start to talk about is what do we calculate with this first order approximation. Thank you.